Okay, fantastic. We have a fairly important problem. It's Monday, we're exhausted, so we're stuck. So, here we go. 2017 Mech 3. The threes are always the free response ones. I mean, free are always the rotation ones. See, I can't keep it straight either. Come on. Alright. Calculate the total kinetic energy of the cylinder as it reaches the table. Okay. That calculate word means a lot of things. Do you remember any of them? I would start by saying, so that means you have to show all your steps, or they're going to grade some steps. You don't have to use two letters for anything. But I would actually show the equations. mgh equals kinetic energy final. And I would go ahead and list that as 1 half mv squared plus 1 half iw squared, because it rolls without slipping. Let's see. Incline plane, cylinder. No friction energy loss, so energy is conserved. Makes a smooth transition. Let's see. And it rolls without slipping. Okay. I hid it behind my little card there. But it says calculate. Does that mean I could stop my answer with algebra? Oh no. No, it doesn't. In fact, it means I actually need an answer. Whoops. I didn't want that. Okay. But I can just start plugging things in. There's 0.50 kilos. I'm probably okay with 10 for G. Ooh, what is the height? Look at that picture. I can't look at it. It's out of view. Okay. Um, I think they only give the incline, the length of the incline on the picture. Yes, so I have to do 1.0 meters times the sine of 30 degrees. Okay, so I have 0.5 times 0.5 times 10 is 2.5, and that's all the sig figs they gave me. 2.5 joules. Or maybe 2.45 if you gave 9.8. 9.8 is certainly acceptable. It's a little clunkier. Okay, well, that's it. Well, they say part A is probably just 2 points. Using conservation of energy, and then getting that right answer with units. Okay, and they think they were really careful, Alan, to not give enough information to solve that first part any other way. Okay, so you have to use energy. It's the only reasonable thing, based on what they gave. Okay, then part B, they're kind of, so I didn't waste my time writing down that big energy formula. Part B, calculate again what is W, or the angular velocity, in radians per second. The moment it reaches the floor, oh no, well actually, it's not going to increase or decrease rotation. We're probably ignoring air resistance as it falls. So I actually just need its angular rotation and its angular velocity as it leaves the edge of the table. And then we can assume it's the same. So I actually just need this. In this equation that I already wrote down, I need what is that W? Yep. So am I. Well, I like to do algebra first. It's a little faster. We've got mg. I actually want to put L sine 30 because that's what we had to do. Equals 1 half m. Let's go ahead and do r squared w squared because I don't want to forget. Plus 1/4 m r squared w squared. Okay, I put in the 1/2 for the mr squared over 2 for the disk. We've got our mg. Okay, good. M's go out, so rather than plug in my 2.5 joules and kind of risk messing it up, let's do that. Besides, this in whatever units, this is just 5. 1 meter times a half times 10. Half of 10 is 5. I need the radius of the thing, which is 0.1 meters. Okay, but I can see also that I have a half plus a fourth, which should be 3 halves. So G, just showing an intermediate step that maybe if I'm a super genius I don't need to show. Oh yeah, that's even GL over 2, because I do know what sine of theta is. And then I have 3/4 r squared w squared. So W multiplied by the 4 is going to be 2/3 GL over r squared, and take the square root, equals W, and that's automatically in radians per second. Okay, so now I did a bunch of algebra. It says calculate. Rats. So maybe there's points for substitution. So you should drag yourself through it. 2 times 10 times 1.0. I didn't say units. It says units are only ever counted on the final answer. Times 0.1 squared. Take the square root of that. I'm going to cheat because I don't have time for the calculator. And they say 25.6 with an extra sig fig. Boo. Rads per second. Okay. Could you follow that? Sure. That's right. There's now no longer, so give ourselves an extra week. Rolling down the incline, there's a torque. Remember those section 2 problems I did? Friction between the table and the rolling object is providing a torque and speeding it up. As it rolls without slipping, so it spins faster and faster as well. It has to. But then once it leaves the table, it's just going to rotate. It can't change angular momentum anymore. There's no more torque from the air, right? I could even argue with a uniform cylinder, it should be the same. No, it should actually slow down a little bit. But okay, we'll neglect air resistance. It rotates the same even though it falls faster. Gravity will pull it down faster and faster. So it becomes a projectile. But physics doesn't care that it's rotating. The rotation stays the same. Yep. Let's see what the points were for setting the kinetic energy equal to the sum of linear and rotational. So there was a point just for that. Just for having this piece that has them both. That was a point. For substituting into the above equation for linear velocity and moment of inertia. Yep, okay, so RW. Like I correctly switched to RWs. So actually, and for the 1/2. So if I had missed that half, I lose a point. Okay. Ooh. And it's a good thing that occurred to me, because correctly substituting into my equation, that was the point. This time, no points for the excessive sig figs, radians per second with units. So part A, there was a point for the correct answer with units, because it's relatively simple. For this one, it's just showing the correct substitution, which if you calculate correctly, automatically yields the correct answer. They do like to alternate. Okay. Okay, for part C, I think you can handle it. Calculate in joules the rotational kinetic energy and divide it by the total kinetic energy. So total, do the whole thing. Oh wait, and is it at the floor? Or is it leaving the table? I can't read. Anybody still need this slide? I think it's on my next slide. Okay. the cylinder the moment it reaches the floor. Okay. So it is a little bit hard, but I'm sure you can handle it. The rotational kinetic energy will be the same as we just calculated, so calculate only rotational. And then you'll have increased kinetic, so you started with some kinetic energy as you leave the table, that's in part B, and then you increase. You have mgh more, but that's linear only, so you only add that part to the total. You don't do the rotational. You leave it the same, and then calculate the horizontal distance. Well, you go back to part B, you had radial. Well, at the end, right here, your V just equals omega times R. So your 25, whatever answer you got for part B, for this W, multiplied by the radius, that's also your linear velocity, and now you're a horizontal projectile. You left the table at that velocity, all in the x direction, and now it's a classic, like, it's the first unit that we did. You fall 1.75 meters, starting from rest vertically. That takes some amount of time. In that amount of time, how far do you go vertically, or horizontally, excuse me. That's it. Right. 1/2 gt squared equals 0.75 meters. Your delta x equals v times t, the same t. Okay, yeah. That's what we need to plan a day. Let's work with Peter when you can get some sleep. Because this test that has rotation on it, and it's a big feature, right? Rotation, I especially like the one with 3 spokes, so it's a little easier than that. The free response is one of these rotation ones, so we have to be ready. But the multiple choice is like all 4 topics so far. It's got energy, it's got momentum, it's got projectiles, it's got vectors, it's got everything up to now, and it's got like a smattering of rotation. So you could get by, actually, not doing so hot on rotation multiple choice. Especially if they're too hard, they're too confusing, we haven't had time to practice. That's all true. You'd be okay, because the old problems are there too. That's why we're doing so many free response here at the end, because you got to do a free response out of rotation. And I'm giving it away too. You've got to solve it with change in energy. Okay, you got to solve these with change in energy. You've got to. It rolls without slipping, and there's a change in energy. We should talk theoretically about we did some homework problems where a pendulum swings with a change in energy. Or we have a bar that's pinned and it swings down, and you can get its change in energy. Okay, something that's kind of nice, something that's pinned and swings only has rotational kinetic energy. Because every part of it, none of it can move because it's pinned at an axis. None of it can move unless it rotates. Okay. Any questions, or you think you can finish from there? We have almost 15 minutes. I better clip my video. Okay, well, let's stop this. Okay. Now a sphere is rolled instead of a disc. Oh, okay. You can, considering there's little to no penalty for getting these wrong, just make sure you eventually figure out what it is. And that's something we could take a class or half a class and try. We could go roll things. That's what honors gets to do today.